So my name is Riedinger. I'm a professor of physics for the last 47 years. And I direct the Bresson Center, which is on this floor of this building. And the Bresson Center has two PhD programs between UT and Oak Ridge National Laboratory, one in energy science and engineering, and one in data science and engineering. So that's what this floor is. So I generally teach, I teach every year in this room, next class period, an energy technology course for our first year graduate students in the energy PhD program between UT and Oak Ridge. And, but now this fall, I thought I would teach another course, this one. So this is an honors course. For those of you at Oak Ridge, the background of this is the university has a whole batch of our best and brightest undergraduates in an honors program. I'll have each of you introduce yourselves in a moment. And honor students here are majoring in something, and then they're also have to take a certain number of honors courses. And so what I proposed to Rebecca Page is that we do an honors course on this topic, the science and history of the Manhattan Project. In my field is nuclear physics. Done a lot of experiments at Oak Ridge National Lab, other national labs in nuclear physics. For the last 20 years or more, or 30 years, I've been working on the partnership between UT and Oak Ridge National Lab. So things between university and lab are one of my key passions. And also the history of this partnership, the passion of mine. Well, the history of this partnership dates back to the Manhattan Project. And so that's why I thought I'd do this course. So before we proceed, let me start to introduce other people. Yeah, I'll let you project that. Right. So, what we want to do in this course is talk about the Manhattan Project and what led up to it. And, here's a brief historical review. And we'll go through this in more detail of the science that happened, the politics that happened that led to the Manhattan Project, ending World War II, so on and so forth. And there's a lot of key science goalposts, mileposts along the way, but one key one was 1932. James Chadwick discovered the neutron. And we'll go back into this in more detail, but after Rutherford's experiment in Manchester, we knew that the nucleus had a proton that gives the charge, electric charge of the nucleus, and that provides the stability of the atom. But then the people knew there had to be something else in the nucleus to give enough mass to give isotopes, isotopic variation. And so finally in 1932, James Chadwick discovered the electron. Well, that was a key thing. So the electron is a nuclear particle, but it has no charge. Then Fermi, Enrico Fermi, the great Italian physicist, started a series of experiments in Rome, bombarding every element in nature with weak beams of this newly discovered neutron. And along the way, he found new isotopes, new elements. When he got to uranium, he thought he bombarded uranium with neutrons. He realized that he made something new. He assumed he had made, for the first time, something beyond uranium. Uranium element 92 is the heaviest element in nature. And he got a Nobel Prize in 1938, in part because of that discovery. Well, at the same time, of course, the world was coming apart. Hitler became Chancellor of Germany in 1934, War II, and immediately started enacting anti-Semitic laws. When the first set of anti-Semitic laws were passed, public employees, like professors who were Jewish, had to resign their positions. This led to a flux of wonderful Jewish German scientists leaving Germany, coming in part to the US and to England. In 1938, Hitler invaded Austria. We'll talk about Lisa Meitner later. Lisa Meitner was an Austrian Jew leading a laboratory in Berlin. But she had to leave. She was safe in Germany, leading her group in Berlin, looking at this conundrum of what happened, what do you get when neutrons hit uranium, that Fermi had discovered in Rome. But after Hitler took Austria in 1938, in March of 38, she had to leave and go to Stockholm. Her group continued, however, and the seminal experiment was in December of 38, when they realized that when you hit uranium with neutrons, it is not that element 93 or 94 had a chemistry of barium, which is what Fermi proposed. It was in fact that you were making barium. Well, how could you make element 56, barium, about half the weight of uranium, by hitting with a very slow neutron? The answer, people finally realized in the next couple of years, it was nuclear fission. And people could then quickly do a back of the envelope calculation saying that if uranium split into two rather equal pieces, there'd be a rather tremendous release of energy. That led, after a circuitous route, to Einstein, who is now in Princeton. He left Germany, but he's Jewish, he was Jewish. He wrote the famous letter to President Roosevelt in 39 saying, there has been a discovery of a newfound process that we're calling nuclear fission. It is possible that this could be harnessed into the greatest weapon the world's ever seen, and Germany is certainly working on this. And so that emphasized the importance of what came to be the Manhattan Project. However, nothing happened for a while in the US. England was pushing on us to get involved. England was under attack. England was worried. Hitler was winning the war. Hitler had taken Belgium and the Netherlands and France. Next was England. And then it all changed on December 7th, 1941, when the Japanese attacked Pearl Harbor. That meant now we were in the war. Soon thereafter, Einstein's letter became more important to Roosevelt, and soon thereafter, Roosevelt started a project, the Uranium Project, to see if we could do something about harnessing nuclear fission into a weapon, because everyone knew the Germans were working on this. And if they got there first, they would have won the war. No doubt, in my view. I'll have Ray talk about this in a minute, but then this resulted in 1942, fall 42, the Feds picked what we now call Oak Ridge as the place where you can locate. You can nestle a secret laboratory in the hills of East Tennessee. TVA had just built Norris Dam in 36, so there was all of a sudden, for the first time, rather abundant electricity in East Tennessee. You needed that for a secret laboratory. You could, put it in the hills of East Tennessee, and few people would know about it. It's not so far from Washington. Less than a year later, the graphite reactor opened. We'll tell you something about that. That was crucial for the Manhattan Project. And of course, eventually that led to the atomic bomb being built. Los Alamos was involved. Of course, that's where the weapons were designed and built and tested based upon work done at Oak Ridge. And then finally, the bombs were dropped on Japan. So that's it to end World War II. That's the broad outline of the history. And so this is a great topic, in my view, because it's great discoveries in science, primarily in physics, in the first half of the 20th century, happening at the same time as world politics going haywire because of Hitler, primarily. And it's an interesting story where the history affects the science, and the science affects the history. And that's what I want to talk about this semester. I guess, right, so part of it is, I mentioned fission. I should have shown this before. when a slow neutron hits a big uranium nucleus, gets absorbed, and then uranium-236 splits into two pieces, and you get energy off. That's the nuclear fission process, and that's a lot of energy. And people calculate very early that 1 kilogram of uranium enriched in the proper isotope would have the same energy content as 2,700 tons of coal. Wow, that's remarkable, and that's because the nuclear force is many, many times stronger than the electric force that holds the atom together. So people realized right away after the seminal experiment in Berlin in December of '38, people realized that if you could control this nuclear fission process, you could release a whole lot of energy. Another crucial thing was people realized possibly of a chain reaction. We'll talk more about this. In other words, when uranium fissions due to absorption of a neutron, you get not only fission fragments, 2 nuclei, which is about half of the mass of uranium-235, but you get 2 or 3 neutrons emitted. Well, if you can slow them down, moderate them, or whatever, they can cause other uranium nuclei to fission. And voila, you get a chain reaction. And part of the physics being looked at very rapidly in the late 30s, early 40s was how rapid is this process? Would that happen in minutes or in microseconds? And people in England did this calculation that this chain reaction could be very fast. And that means that you could theoretically build a bomb because of those neutrons being absorbed by other adjacent uranium nuclei. It took a while to figure out the physics of this. Somewhere along the line, people realized that you could also use plutonium. Plutonium-239 is produced in a reactor, by the way. If you build a reactor, and that's what the purpose of X10 in Oak Ridge National Lab was, to build a reactor to absorb neutrons on uranium-238, then it would decay. Uranium-239 would decay to neptunium, then plutonium. Plutonium does not exist in the ground in nature, but if you could make it, create it in a reactor, if you could build a reactor, you could read plutonium-239. And plutonium-239 also fissions. And the advantage of plutonium-239, it gives off 2.9 neutrons per fission event, whereas uranium-235 gives off 2.4 neutrons on average per fission event. So if you could make plutonium in a reactor, if you could build a controlled reactor, then you might be able to make not only a bomb based upon fission of uranium-235, or you could build it on plutonium. And we want to talk about that. That was part of the Manhattan Project, the rush. I got diverted. I opened up the wrong file here. I wanted to go to this first. I got started on something I didn't intend to. Before I get started on that, I wanted to introduce Ray Smith. Ray, come up here for a moment. So Ray Smith is about my age.
Yes.
I've been here on the UT faculty for 47 years. Ray worked at Y12 at Oak Ridge for a mere 48 years, and then he went to retire.
That's correct.
But he is not sitting on the couch. He was, before retirement, the historian of Y12. Now he's more broadly the historian of the Manhattan Project broadly, the historian of Oak Ridge broadly. So Ray gives lots of talks about the Manhattan Project, the history of all this. He's going to do this with me.
Lee, my wife Fanny says she can't tell any difference. after retirement.
Okay.
So I am staying busy, obviously, but I'm enjoying it. I'm getting to do the things I like. It's fun.
Yeah, so Ray, I'll call you back up in a minute. I got started on the wrong file there.
That's okay.
So went right into the story. I forgot to
Oh, you're fine.
introduce Ray. So Ray these are Ray's accolades, all of what he does. You know, he's a very active guy. By the way, there is something called the Manhattan Project National Park that is a virtual national park based on sites that were key parts of the Manhattan Project. Oak Ridge, Los Alamos, and Hanford. And Ray is one of the critical parts of that Manhattan Project National Park. And that will come up too. So Ray does a lot of different things. And he's been recognized for doing those things. He got a gold medal for his work in creating that Manhattan Project National Park. So it's great to have Ray involved in this intimately. And so before I got diverted, I mean, this course is important to me because Oak Ridge would not exist if it were not for the Manhattan Project. And UT would not be as good of an institution if Oak Ridge did not exist. In the areas of science and engineering, for sure, University of Tennessee is a better institution because these Oak Ridge laboratories are 27 miles away. And of course, nuclear energy, nuclear weapons, nuclear medicine are all things that we know about, and they all emanate from the race to build the atomic bomb in the Manhattan Project. After World War II ended, the emphasis on things nuclear was focused on energy, on medicine, on weapons of another generation. And so it's a neat course to me of mixing science and history. The book I want to use is this one. Richard Rose, Ray, and Richard are on committees together. You just were in a meeting yesterday, you said.
That's correct. Common Heritage down there.
So this is a very good book. It's a very readable book to me. Not a science book, but he mixes in science with a whole lot of history. And so that's the foundation, that's the basis that we will use. I'll try to guide you through this book as we go through our lectures of what part I'm talking about. You know, this is cheap. You can get this off of Amazon for $10, I think. So we want to, these are the different components we're going to talk about in this order: the revolution in physics, those great discoveries, figuring out fission, the Manhattan leading the Manhattan Project. There's a lot of history concerning the decision to drop the bomb on Japan. Germany surrendered in May of 1945, so that ended the European part of World War II. Roosevelt died in April of 45. Harry Truman, the vice president, became president the next day. After that, he was informed of the Manhattan Project. The vice president knew nothing about it. That's how secret this was. It was then Truman, in the summer of 1945, that had to decide what to do. You know, the Japanese said, the Japanese knew that we invaded Europe, leading to Germany's surrender. The assumption was that we were going into Japan. Indeed, my father was in the Philippines, almost surely part of the invasion force. We were going into Japan. And that would have been really a bloody, difficult invasion because the Japanese said, let them come. We'll fight them door to door. That led, therefore, to the idea to drop first one atomic bomb, uranium bomb, on Hiroshima, and the second, 4 or 5 days later, the plutonium bomb on Nagasaki. And finally, then the emperor took control and forced the idea of surrender on the crazies in the Japanese government that said, let them come. They don't have any more of those big bombs. And so they surrendered. Only then the people in Oak Ridge realized that they've been working on it for the last 4 years. Terror drove the Manhattan Project to a large extent. Terror that the Germans would get there first. We had no idea whether the Germans had progressed much toward an atomic bomb. It was not until Germany surrendered that our scientists got into Germany and found out they didn't get to first base on their atomic bomb project, on their Manhattan Project. They were working on it, but they never made it to first base really. And so, but we didn't know that. And we'll talk about that later too. After World War II, after the atomic bomb was dropped, there was a long period of, or some period of even Oppenheimer, the leader of the Manhattan Project, having second thoughts about actually using the weapons. A lot of debate about whether we should have done that. And so that led to then an arms race. We can touch on that. And that then led also to the peaceful uses of nuclear energy. So it's a very rich history. You 6 need a grade. Mary does not need a grade. And here's where I thought we would do it. I think that I have a test at the end of the semester. Along the way, I would like for each of you 6 to give a little talk 4 times during the semester. You know, there's about 4 times 6 is 24. There's a little bit more than 24 classes. So starting next week or maybe the week after next, I'd like to have each of you, and I'll help you suggest topics relevant to where we are in this progression. Give your own talk. I don't know, 10, 15 minutes, whatever, about that you would then read up about and present to the class, to everybody out there in either land too, about what you learned. Maybe it's people. Marie Curie is a critical part of this. Enrico Fermi. There's the Hungarians. I think this is a great story too. Just great book, Martians of Science, because Szilard and Riedinger and von Hevesy and who else, Ray? There were 6.
Von Neumann.
Von Neumann. Yeah, there were 6 Hungarian Jews who grew up near Budapest. And persecution of Jews in Hungary that in the late 1800s was pretty extreme. They emigrated to Germany, got their scientific training, their degrees in Germany. And then Hitler came along. Then they had a new Germany. And these 6 became cornerstones of science and technology primarily in the US. And people often wonder, how could that be that these 6 came from this middle-class part of Budapest in the late 1800s? Well, so there's a book about that. 5 physicists who changed the 20th century, all Hungarian. Anyway, so there's a lot of different stories that you all could write about. I think you should each present 4 little talks along the way, and 2 of those you should write up into more major term papers, so to speak, that you would hand in. That plus a test plus class participation is how I would determine grades. We have fall break on October 4th. We'll get class then. Ray and I will organize some tours of Oak Ridge facilities. Have you seen some of these things? You might get to see that again.
Literally to do.
Right. Like the graphite reactor. And so that's how I want to do the class. Any questions or comments? Okay, well, now I'm going to go back. I got diverted. I want Ray to come up in a minute, but I just want to go back to this. Oh, by the way, people in Oak Ridge, are willing to interrupt and ask questions and make comments, you 6 do not necessarily have firsthand experiences, except through maybe your father that works at the laboratory. But Mary spent 30 years living in Oak Ridge, and people sitting in Oak Ridge, some people there are worked on the calutrons, so they all have their own experiences. And so I welcome, encourage their comments and input at any point along the way. So just any of you in Oak Ridge or anyone here, just pipe up if you have a question or comment. So back to my overview of the historical development. Robert Oppenheimer, we'll talk more about him. There's books written about Oppenheimer, a great physicist, a Berkeley physicist, Jewish, grew up in New York City, sickly boy. His parents immigrated to the US from Europe, and he was a good student, but he was weak and sickly, and so they sent him out west to New Mexico to toughen him up when he was a kid. He then got his PhD working in Riedinger in Germany, and went to the faculty at Berkeley. Berkeley was not a high-class institution in the 30s. It was the new physics department. Very broad guy, read poetry and all that. Handsome guy, ladies' man, good party guy. And it was common in the 30s, a lot of intellectuals dabbled in the Communist Party. He dated for a while a lady who was a member of the Communist Party and active in the Communist Party in the US. He married Kitty, and she had been married before she married Robert Oppenheimer. She was married to a Communist Party official in the US, and he was killed fighting in Spain. And Kitty had been a member of the Communist Party. Oppenheimer was never a member of the Communist Party, but he ran in that crowd. He was the most respected American physicist in most ways. And the issue was when the US, when Roosevelt decided we are going to start a uranium project that came to be known as the Manhattan Project, who would lead it? Couldn't be a military guy, had to be probably a physicist that had great respect and great capability. Oppenheimer was the choice. And his partner in this, strange partners, was Leslie Groves, the general. So here was a intellectual, a urbane European type intellectual as a physicist, and this hard-nosed, hard-charging general. People, Leslie Groves had helped taking the lead on building the Pentagon. And so he was a doer, he was an achiever, a no-nonsense kind of guy. His security people told him, you can't choose Oppenheimer, he may be a communist. He certainly is married to a lady who may have been a communist. So his security people said, do not hire Oppenheimer. But the point was that there was no better choice available of a physicist that could lead this complicated technical project and have the respect of the hordes of scientists you would pull into this project. So it worked. It was tough, it was difficult, because Groves and Oppenheimer were such different people. But it worked. And we'll talk more about that. Groves, when he took our project, immediately realized that a lot had to be done. This was 1942 now. After Pearl Harbor, we were in the war. The Germans were progressing rapidly, both on the military front, and we assumed learning how to build an atomic bomb based upon uranium. We'll talk more about this, but there was a supply of uranium ore that was sitting in Staten Island. Somebody had imported that to the US from the Belgian Congo before the war. got to it before the Germans got to it. And so that was lucky for Grove when they figured that out. And so that was key for the Manhattan Project. Grove sent somebody there to buy that stockpile of uranium ore, which was crucial, sent to Oak Ridge, crucial for our project. Grove decided that he needed a place to build a secret laboratory. And he then approved request to buy 52,000 acres along the Clinch River in East Tennessee. And about the same time, this was happening. You see, Fermi was not Jewish, the Italian physicist who first started the process to understand nuclear fission, got the Nobel Prize. He wasn't Jewish, but his wife was Jewish. However, her passport, by mistake, was not stamped Jewish in Italy. So when he left, he and Laura left to go to Stockholm to accept his Nobel Prize in the fall of '38. They were able to leave fascist Italy, but somebody had never stamped her passport as Jewish. When he got out that way, he came to the US. He was part of the Manhattan Project, first in Columbia University, then in Chicago. In Chicago, he wanted to see if multiplying neutrons, if a chain reaction would work. So they assembled a pile of uranium, 458 tons of uranium oxide, 6 tons of uranium metal, 400 tons of graphite. You see, to make a chain reaction, they knew you may have to slow down the neutrons that come from fission of uranium in order to make them cause other adjacent uranium nuclei to fission, make a chain reaction. That's what the graphite is about. So this is an experiment they did in Chicago. The University of Chicago was a founding member of the Big Ten athletic organization, but they shut down football less than a year before this. So if the place where he built this pile was under the football stands at the University of Chicago, South Chicago. And that worked. So it went critical for a few minutes, December the 2nd of 1942, and that meant the next step needed to occur. In this alternative array, the next step was to find a place where you could build a reactor, scale this up, build a sustained controlled reactor that you could use to breed plutonium in the Manhattan Project. You want to come up and start the story, right?
Yes, I'll be glad to. It's an interesting story, and I've often had the chance to introduce to people this transition that took place in Oak Ridge. On one occasion, we got to interview Senator Howard Baker. You all know he's passed away now, but for many years he was a staunch and strong political personality here in Oak Ridge. Had his office up in Scott County at Huntsville. We took a television camera up there. Back then you had to carry a large camera. A few years ago. Now we just do it with an iPhone. But we did set it up in his office and said, "Okay, Senator, tell us about your connection to Oak Ridge." And he said, "First, let me tell you how that place was chosen." So I said, "Okay, good." So he started out. He said, the way it happened is that they had these ridges and valleys in East Tennessee, and they thought they could put the factories down in the valleys, and the ridges would protect them if one of them blew up or something. And as Lee mentioned, it's just down the river, the Clinch River, from about 20 miles from the Norris Dam, completed in 1936. But what all of this is considerations going on when General Groves and others, they've been looking at it several months before Groves actually made the decision in September of 1942 to purchase the land. But Senator Baker said, what may be closer to the truth about how that place was chosen is that when Albert Einstein wrote that letter to President Roosevelt saying Germany is buying up all this uranium ore, And he was afraid they were trying to build a bomb out of it. Roosevelt knew it would be an expensive undertaking. So he put General Groves in charge of the Manhattan Project, as Lee mentioned. Groves had just finished building the Pentagon, so he knew how to put a large construction project together, knew how to get private industry involved, and he knew how to spend money. So President Roosevelt also called in Senator McKellar, and he said, Senator, I need to put a large amount of money against the war effort, and I can't let the press or anyone know how much it is or what it's being used for. Can you help me with that? Senator McKellar said, yes, Mr. President, I can do that for you. Just where in Tennessee are you going to put that thing? Now, that likely had more to do with this area getting selected for the Manhattan Project than any ridges and valleys or proximity to a dam. When the senator got through, I said, thank you, sir, for putting on video the story that I tell everyone who comes to Oak Ridge. He looked at me and he said, where'd you get that story? I said, I got it from Dick Smizer, longtime editor of the local newspaper there, the Oak Ridge. He said, that's where I got it too. Now, I'm going to tell you another Senator McKellar story, and I know this one's true, because the man that it happened to is still alive today. His name is Lester Fox. He's the patriarch of the Fox automobile dealerships in this area. But in 1942, he was a sophomore in high school at Oliver Springs, a little community just north of Oak Ridge, or where Oak Ridge is today. Now, he was skipping school. Him and his buddy were playing the pinball machine. When they got through, they were walking down the main street of the little town. They walked by the telephone office. Now, you all have to understand, back then, everybody didn't have a cell phone. There was only one phone in the entire town. It was in the telephone office. So as he was walking by, him and his buddy, the telephone operator leaned her head out and said, Lester, go get the principal. He's got an important phone call. Now, Lester's skipping school, but he does. He goes and gets the principal. Principal comes over and takes that phone call, comes back to the school, calls all the students together in an assembly, and says, I've just gotten a phone call from Senator McKellar. He wants me to tell you to go home and tell your parents you're going to have to find another place to live. The government's going to take your property for the war effort. Now, Lester swears that's the way these 3,000 people first learned they were going to have to get off of 60,000 acres, nearly 60,000 acres, in order to make room for the Manhattan Project. Many of them didn't have automobiles. They didn't have trucks to move their belongings. If they had a car, they might not be able to buy gas for it, or tires. Those things were rationed. So what they did have was young men in the military getting killed. So they wanted to do anything they could to stop that killing and to end the war. So they got off of their property in a matter of days, some of them. In November of 1942, October, November time frame, they got letters tacked up on their doors, said they had a matter of days, a couple of weeks, to get off of their property. So those 3,000 people had to leave in order to make room for that Manhattan Project. Now, what he's showing you here is the fact that the Manhattan Project was much more than Oak Ridge, but Oak Ridge was 60 cents of every dollar spent during the Manhattan Project was spent right here in Oak Ridge. The primary purpose for Oak Ridge was to get to separate that uranium-235 from uranium ore. Now, the thing you have to remember is in uranium ore, there's only, in 1,000 pounds of uranium ore, there's only 7 pounds of it that's uranium-235, 0.7%. So you've got to separate that little bit of uranium-235 out to get the part that you need to make an atomic bomb. And also, as Lee mentioned, the British first realized that this could be done. But they realized also that it was going to take a huge amount of resources to actually put all of it together to get more than just laboratory quantities of the uranium-235. So they literally sent their scientists over to the United States, along with several others that were pulled together by General Groves and by a large committee that was working there as well. But they said, look, the United States, you make the bomb because you've got the resources. I look at all of the resources that literally had to be put together to make that atomic bomb. And it took from 1942 till August of 1945 to get that done. Now, that's where the start was, and see what your next one is. This kind of gives you the layout of the Oak Ridge site. And what you see here are those ridges and valleys. They run from northeast to southwest. And it's 7 miles wide, 17 miles long. And the closest town to the area, and an interesting side note is when they were naming this, the first name chose for it was the Kingston Demolition Range. That didn't last long because it had a very ominous sound to it, and Kingston was the city down on the south and west of it that it was named for. But they quickly decided to change it to another name, and what they chose was the Clinton Engineer Works because Clinton was the nearest city to the area they were chosen. Now, this is something that the Corps of Engineers did routinely. They would take, and as they named their districts, they would name it for the main city in the middle of their district. Now, when they started the Manhattan Project, the main city that they were using was New York City. So they named it the Manhattan District. Then when they changed it to be the Manhattan Project, they just kept that Manhattan name and called it the Manhattan Project. So when asked how did the Manhattan Project get its name, it's because of the Corps of Engineers' approach to naming their districts, the Manhattan District. General Groves moved the headquarters from New York City down to Washington, D.C. But actually, Colonel Nichols, who we'll talk to you about in a lot more detail, he actually ran the Manhattan Project, all of the day-to-day activities from right here in Oak Ridge. With the exception of the Los Alamos, the scientific part that Robert Oppenheimer ran, he was reporting directly to Groves for that. But all of the administrative day-to-day activities, Colonel Nichols actually ran that from Oak Ridge. So the Y-12 site is located here just across Pine Ridge from where the city of Oak Ridge is. And then across Chestnut Ridge, you've got the X-10 site of the Oak Ridge National Laboratory. And then over farther to the west, you've got the K-25 site, which had not only the K-25 gaseous diffusion, and we'll talk about all of that as we get on into the details, but it also had the S-50 thermal diffusion. So there were 3 approaches to getting the uranium-235 that was needed. And there's good reason why that thermal diffusion was used. And gaseous diffusion eventually turned out to be the way that we've gotten all of the highly enriched uranium that we use in nuclear weapons today, rather than the Y-12 approach, which is the electromagnetic separation. And we'll get into lots of those details a little later on. But let me introduce the idea of these sites by asking you a question. What does Y-12 stand for? And you people in Oak Ridge, you can't answer that because you already know. But these young ladies and gentlemen here probably don't. No idea, right? You do. Somebody always guesses that. On the grid on the map that has an X over the X-10 site, the Oak Ridge National Laboratory, and a Y over the Y-12 site, K over the K-25 site, didn't exist until 1970. It's an emergency response map. And no, the coordinates of a map has nothing to do with these names. Y-12 doesn't stand for anything. Okay, it's just a designation for that location. The same thing I believe for X-10, doesn't really stand for anything. There's some speculation about that, but I think we have some pretty good evidence that K-25 stood for, or might stand for, the Kellex company, which is the company that made the gaseous diffusion equipment, that'd be the K. And then the 25 was known to be a shortcut name for uranium-235. They took the 2 off the right-hand side of 92, the atomic number for uranium, and the 5 off the right-hand side of 235. They called it 25. They did the same thing with plutonium. They took the 4 off the right-hand side of 94 and the 9 off the right-hand side of 239, and they called it 49. Now, there's a fellow who's written a book not too many years ago, Jeremy Bernstein. The name of his book is Uranium, the World's Most Dangerous Material. On the front cover of his book, he has a huge watermark of a 4 and a 9. So he knows the story. But Y12 doesn't stand for anything. How's that for an overview and an introduction?
So who chose those numerals and letters, do you think?
Interesting you should ask that. Who chose those designations? In General Groves wrote a book, Now It Can Be Told. And in that book, he addresses that question. And you know what he came away with? I can't remember. It just came about. So I don't know. I've tried to research that. Where did those codes come from? And I've not been able to identify a source for it. Now, the Los Alamos project was the Y project. Oak Ridge was the X project, or X location. And Hanford was the W. So I don't know, was Y feeding to the Y project in Los Alamos? I can't make that connection. So the short answer is neither General Groves nor I remember. Or he doesn't remember and I don't know. Talk a bit about the Oak Ridge graphite reactor. Would that be good? Sure. So this is where it's located. It's still there. Looks just like that today. It's actually a National Historic Landmark. And it's a part of the Manhattan Project National Historical Park that Lee mentioned earlier. That park consists of locations in Los Alamos, Hanford, and Oak Ridge. In Oak Ridge, the headquarters is up at the Children's Museum. But it has responsibility for and has designated sites within that park that include the graphite reactor. Over at Y12, it includes what we call Beta 3, building 9204-3, close to Eva Hickman's heart. Eva, I know you appreciate that, and you can interrupt me anytime you want to add something more about Beta 3, but she did work there for many years and knows a lot about the building. But it's the one that still has the only racetrack, full racetracks of beta calutrons in existence. And we'll get into a lot of depth and detail about what those are a little later on. But a building 9731 is also in the park at Y12, and it has the only alpha calutrons, big, large, about 20 feet tall magnets that were there during the Manhattan Project. And then the K25 footprint, at one time the world's largest building under one roof. Now all that's left of it is a U-shaped footprint. But they're building a history center there in the second floor of the fire department, and also going to have a replica building that will show you what the K25 building looked like in a little slice of it. That'll actually have some replicas of the gaseous diffusion equipment and a viewing tower so you can see the U-shape of the footprint. All of that's in the works and going to happen. Back to the history of the graphite reactor. Actually, it is the world's first industrial-sized nuclear reactor. Now, what Lee mentioned about the Chicago pile was literally a pile of graphite with uranium put inside that graphite to the point that they built enough of it in there that it went critical, that it started producing that chain reaction, and then they stopped. Well, down here with the graphite reactor, they actually did much the same thing. They built a larger pile of graphite, and they drilled holes in it to where they could insert the uranium as slugs, just little pieces of uranium that you can slide in, and you get it into the center and into close proximity. Then those neutrons being given off from the chain reaction and being moderated, slowed a little bit by the uranium, you get enough of that, or by the graphite, you get enough of them together, then you get that chain reaction started. And that started at 5 o'clock in the morning on November the 4th of 1943. They started building it in February of 43 and completed it in November of 43, and actually had the chain reaction going. Now, the interesting thing is that reactor operated for 20 years. They shut it down and 20 years later in 1963, and then it was designated as a National Historic Landmark in 1966. That operation produced only a very small amount of plutonium, enough that they could tell that, yes, this is going to do what we want. But General Groves became concerned, and others, I'm sure, about putting all of their eggs in one basket, if you will, about putting everything here in this East Tennessee location. Also, they realized that not only was the separation of uranium going to be a long, slow process and require a lot of resources, and they didn't know whether the gaseous diffusion process or the electromagnetic separation process, which one's going to work the best, which ones are we going to be able to use. And when they were building Y12, they got about half of it built, and they realized it's going to be so slow. They said, just move down the valley and build another building using the same drawings that you had to build one of the other Alpha buildings, Alpha 4, Alpha 5 and Alpha 4, 9201-4, 9201-5 are identical buildings, because they said, we're going to have more capacity. Just move down the valley and build another building. That kind of thinking, they realized, look at this producing of plutonium, we're going to need more than one reactor. We're going to need a lot of it. And the other thing is they had used air to cool this one. When you get that chain reaction going, you produce a lot of heat. And they needed to cool it down so that it wouldn't melt, if you will. So they was using air. And they realized that's probably not the best approach. Water might be better. So that's why they chose the site out in Hanford, Washington. Over 500 square miles. The Columbia River is there. And they built 3 large reactors.
There's a slide on that few hints. There's a slide on that.
The next one?
A couple more down. There's Henry.
So yes, that's the F reactor. They were all very much alike. The B reactor is the one that's still there today. Now, it's not operating anymore, but it's a part of the Manhattan Project National Historical Park. And those reactors were built along the Columbia River, as you can see. And because of that need for large space, they didn't keep everything here. They moved it out to Hanford, those 3 reactors, in 1943. Now back to the graphite reactor. The interesting thing that we have to realize there is they didn't use that plutonium, but they had that reactor. And the scientists immediately realized that there's value in having a reactor and using that reactor for producing other radioactive materials. And that's what, for 20 years, that reactor produced isotopes, radioisotopes. And you can actually, the front of the reactors where you load the uranium in, over on the side, you can actually put in material that you want to get in close proximity to those reactions and to produce radioactive materials from that reactor. That's where nuclear medicine actually came from, is the graphite reactor. Taking some of the isotopes separated in the calutrons at Y12 and running them through the graphite reactor to get other radioisotopes that were used for nuclear medicine. You want to talk about that, or you'd like me to?
Go ahead.
So this is Ernest Lawrence. Ernest invented this calutron. Calutron actually comes from the name California University Cyclotron. And he was out in Berkeley, California, and had been working with the centrifuge. And he had the idea that you could separate uranium in using this physics process. And he was a good promoter. He really promoted the idea to Groves, even though Groves was a little hesitant and wanted the gaseous diffusion process, thinking that that would be the more effective means, which it ultimately turned out to be. But you have to realize, here they are thinking that Germany is building an atomic bomb, and they're in a race with Germany in their mind. And Groves feels like he has to use every avenue that he can find to try and figure out this first time ever done experiment about how to separate this uranium. This one is very simple in its process, and that's what made it so attractive, and that's why Lawrence was able to promote the idea of how it could be done. Now, the way it works, again, a very simple process, no moving parts in it. You just take this uranium chloride mixture. Now, the way I explain this to people, and they seem to grab it real quick, so I'm going to use the same approach to you to show you how this separation takes place. If I had two rubber bands hanging down from my hand, and I put a golf ball on one and a ping pong ball on the other, then I held it to my side and just spun it real quick for a half a turn, that golf ball would stretch that rubber band further than the ping pong ball. So I get two arms. Well, the same thing happens with uranium-235 and 238. Because there's 3 neutrons difference in the mass of the 238 over the 235, centrifugal force will make that 238 ion make a slightly larger arc than the 235. Now, what makes it make the arc is the magnetic field. And in the calutrons, the way they're set up, this is what's called a racetrack. And there would actually be 96 alpha calutrons. Alpha is the first stage, beta is the second. And between each of these magnets, you'd have a vacuum chamber. That's where the actual arc takes place, is in the vacuum chamber between the magnets. So the material goes in at the bottom as a uranium chloride ion. It's ionized, so it's attracted out electrically out into the vacuum chamber. Once it gets into the vacuum chamber, the magnetic field causes it to bend. And you can catch the two ions, major ions in the mixture, by putting just collectors up there to catch them. Now, the secret is that you've got to get them adjusted just right so that it actually gets that. It's a very inefficient process, actually, in that not as much of it as you'd like goes into those slots. But remember, in 1,000 pounds of uranium ore, there's only 7 pounds of 235. So you've got to run this through, and it's batch processes. You've got to run it through a number of times and through a lot of processes. They actually had 1,152 of those calutrons in 9 large buildings at Y-12. And it actually took from, they started construction of Y-12 in February of 1943, and it was February of 44 before they produced the first quantity, about 200 kilograms or 200 grams of uranium that could be shipped out to Los Alamos. Lee, there's an interesting story about that little bit of uranium. Bill Wilcox, you remember Bill? He was the chemist working at Y-12 at the time. And they gave him that first shipment to process. And he took it and put it in a glass beaker that was a funnel shape, and he set it in a metal can. He put it in an oven. The lip of the funnel shaped glass beaker just fit on the top of that metal can. So he put it in the oven, turned the timer on for his oven to dry it out, and left it for the night. When he came back in the next morning, His boss caught him at the front door and said, "You need to go higher. The big boss is looking for you and he's wanting to fire you." Well, Phil didn't know what in the world had happened, but what had actually happened is when that oven heated that material up, that metal can expanded, and it let that funnel-shaped glass container fall down into the metal can. Then the oven cooled off, and when it cooled off, the metal contracted, and it broke the glass. So he had glass mixed in with uranium, and they had to start the process all over again. Bill said that's the closest he ever come to get a fire. Now think about it. First, the world's first appreciable amount of uranium-235. And Bill Wilcox was the one that was happening. He was the historian at Y-12, my mentor and a really close friend. So I love to tell that story on video. But this process turned out to be what actually produced the uranium-235 with some feed from K-25 and S-50 that we will get into in more detail when we get into those specifics. So the Alpha plant, the groundbreaking was in February for the entire site. 18th, they started on the building of the first Alpha building, 9204-1. And they had to leave to get out of the way for it. That's what the building looked like at the time that they were being built down in the valley. You're seeing the ridges behind it. And a lot of construction going on. I'll talk just a little bit about these young ladies that was operating these Calutrons. Now we call them Calutron girls. Back then they were called cubicle operators. And this one here is Gladys Owens. Gladys worked at Y-12 from January to August of 1945. And she came back in 2004. When she came back, she saw this picture. This picture was, for many years, was a large picture in the American Museum of Science and Energy in Oak Ridge. It's actually that the museum is closed right now because we're moving it over to the Main Street Oak Ridge location. But at the time, she walked in and saw herself. And she told the director of the museum, said, "That's me." He called me up and said, "Ray, I found you a Calutron girl." Now that was the first one that we found, and we found several of them since then. We're getting down to where there's not many of them left. They're getting on up in years because they were right out of high school, 17, 18 years old in 1943 to 45. That means they're 90 and above today, or pushing that. But anyway, we took her out, set her on one of the stools out at Y-12 and made her picture and gave her a tour, showed her the Calutron, the cubicles where she worked. She said, "Ray, I never did know what I was doing when I was working out there. Can you show me?" Now, there were 22,000 people working at Y-12, maybe 100 of them. The chemists would have known they were working with uranium, but they wouldn't have known what they were doing with it. It's the first time it's ever been done. These young girls, they didn't have a clue. They were just trained to do it. She said she didn't know what she was doing. She said, all I knew was when they trained us, this man came into the room at the end of the class who was obviously somebody important because he was wearing suit clothes. And he said to us, he said, "Young ladies, we can't tell you what you're going to be doing. We can only show you how to do it. And all I can say is if our enemy gets it first, God help us." Now, she remembered that 60-something years later and said, "Ray, can you show me what I was doing?" I said, "Yeah, I can show you, Gladys." So I opened up one of these cabinets. I said, "Gladys, when you were adjusting these knobs," and that's what they did for the 8-hour shift that they worked. They adjusted those knobs to keep the meter on a certain point. If it drifted to a control point, they adjusted it back and worked it up. I said, "When you were doing that, you were changing the value of a rheostat down here." She reached over and tapped me on the arm. She said, "Ray, I still don't know what I was doing, but I know if I had any bobby pins in my hair, they'd just go stick to the wall." You know what a bobby pin is? Okay, I just checking. I didn't know. But anyway, the largest magnets in the world at the time is what they were operating. This is also the picture that Denise Kiernan saw that caused her to write the book, The Girls of Tom City. I know we're studying out of this book, and I don't want to take a thing away from this book, but I highly recommend Denise's book, The Girls of Tom City, as well.
We should probably end, Ray, end of the class period. So thank you all for coming here and there, and we'll continue next Tuesday.